Show me the meaning of being lonely. So many words for the broken heart to see in a crimson love so hard and walk with me, maybe light or fly soon become wild and free. I can feel the sun through every beat. Will be done. Tell me, show me the meaning of being lonely. Is this the feeling I need to walk in? Tell me why I can't be there where you are. There's something missing in that hole.
Hi physics lads and lasses, hope you guys are doing well like every day. I'm here with a very brand new topic today guys. So as you heard earlier, I sang a very famous song which was sung by Backstreet Boys. So it's not all about music today. I'm not going to talk about music or the history of the music. No, that's not the topic guys. I'm going to talk about this instrument. Everybody knows this instrument, but the physics behind this instrument is what I'm going to discuss today. Hold on, everything is ready in my classroom. Let's go to the classroom guys. Guys, now you can see my guitar again, but I'm not going to sing anymore. Instead, I'm going to discuss about the physics behind this instrument. This is a guitar. Right, so all the parts of the guitar has been given in the diagram that you now you are just seeing it. You can, if you want to clarify more, just pause the video and just carefully see the picture, observe the picture, and you can identify all the special parts of this instrument, right? But now, this is what I'm going to discuss guys. The 6 inch, here there you can see 6 strings, and their thicknesses are not very similar, not same at all. They have various thicknesses, 1, 2, 3, 4, 5 and 6. The 6th one is a bit should be more close to this, but it's okay, just forget for a while. And the other one is, you can see the wooden body of this one. It's just like yeah, it's a nice body like this, and there was a fretboard here, but why this wooden body or wooden box part? What's the use of it? What's the why do we use this one as a part of this instrument, right? So those are my concerns today guys, right? And how do they form this sound? That's the first part that I have to discuss today, right? Guys, those strings, so what do they do here is they just, so when you plug this one, imagine this is a, let's take a single string here like this, and then when you plug it here, right, it starts to vibrate in a way like this, and then it forms a stationary or standing wave in this way. It's not a traveling wave, or simply it is not propagating in the string here. Instead, it is just a standing wave or a stationary wave such as this, right? So these stationary wave patterns are not, so there are it's not just a single shape like this. It can obtain various shapes in this way, right? The nature of the wave could be one of so there are number of patterns here. Right, out of these, it could be one of these, right? But I'm just going to consider this one here. This is called the fundamental frequency, or this is the fundamental shape, right? And this is the first overtone, this is the second overtone, alright? So this topic will be much more complicated if I start to discuss this part. So I'm going to discuss that part here now, right? Just forget it for a while, but I just consider this one. And the speed of the wave, which is the propagating wave, so as a result of the reflection of the wave, this stationary wave is formed here. So speed of the wave, speed of this station, not the stationary one here, the propagating wave, depends on merely two factors. So we can derive this equation just by using the dimension analysis here, but I don't want to discuss that part. The equation is simply T over m square root. Here T stands for the tension of the string and the m stands for the linear density. What is this linear density? If you're wondering, so linear density is the mass per unit length of a string. Thicker the string, higher the m, obviously, right? So now you can see here, and we all know that here the V, this equation, wave equation, is a very fundamental but very famous equation. V equals F lambda. V stands for the speed of the wave, and F stands for the frequency, and the lambda stands for, this one is a lambda here, lambda stands for the wavelength of each, right? Okay, now here, the frequency now depends upon, and in the given medium, in any given medium, if the medium doesn't change, if the nature of the medium doesn't change, a wave speed doesn't change. So therefore the wave speed remains unchanged. Here you can just substitute T over m square if you want, but I'm going to write it in this way, here V over lambda, right? And as I said earlier, V is equal to T over m square root, and here you can see, and this is a wave, right? So here, this obtains half of a wave, right? So this length is L, if you consider here this length L, right? So the half of a length, so which means half of the wavelength, half for lambda over L, so lambda over 2 is equal L, so therefore lambda is equal to L here. Right, now you can see a very important thing here, the frequency. If this is, if the sound is produced with this, so simply due to a fundamental tone here, right? So F is equal here 1 over lambda means 1 over 2L and T over m square root. Now you can see the frequency. How would you say exactly this frequency is equal to the frequency of sound here? Yeah, guys, once you start to vibrate this, because of the, due to the vibration of these, the particles which are close, the air particles which are close to the string also starts to vibrate, and this is called the resonate. So there's a resonance frequency, so this is called the resonate. Right, so this obtains, or this one acquires the same frequency and starts to vibrate. But without this, the hero, the wooden body, that noise or the sound which is formed here would have been a very tiny sound. But this one makes the difference. How does it do this change? How does it make a change like that? Simply, this one, you can see this one consists a hell lot of air molecules inside this. So once you plug this one, it is transferred to this, the vibration or that resonate, the vibration is transferred to the wooden box, and that wooden box, as it starts to vibrate, that vibration transfer to the those air molecules also. So as a result of that, this one starts to, all of those air molecules inside this wooden box also start to vibrate, right? So this is called the resonate, right? So as a result of that, now a high intense tone, the high intense sound is produced by this instrument. Imagine without this one, if you just use an instrument or without this box. I'm not talking about electrical instrument, electrical guitars or any other thing here. I'm just talking about this classical guitar or acoustic classical guitar. Without the box, it would have been useless instrument, since the noise or the sound which is formed by or produced by this one would have been a very tiny sound, right? Okay, now here, that's it. Now you can see the frequency depends on mainly 3 factors. What are those 3 factors? First of all, L, the length, the tension of the string, and the linear density. Right, now why do we keep our fingers on the fretboard, or why do we press those strings? Right, this is the factor. Now imagine if you have a string in this way, when you, so this is your fretboard and you are not going to, I don't want this part, you are not going to press it. Imagine for a moment. Now this one is a naked string and freely it could vibrate, and the entire length will be the length of the effective length of this. So as a result of this effective length, now the length is much longer, therefore frequency will be smaller. Now imagine for a moment, instead of that, if you press it from here, now the wave cannot propagate or it cannot pass this point anymore. Now you can see a shorter length. The length becomes much shorter. As a result of that, now the shorter L, the frequency will be much higher, right? So that's not a difficult or complicated side. Everybody can understand easily here this mechanism, right? Okay, and the other thing is, now thicker the string, lower the frequency. Easily you can recognize it, guys. Now imagine this is your very first string, or we call it an E first. You can see it, not E first here, E50 here if you consider. And the E first is the thinnest one you can see here. When you pluck this, the noise is much, actually it's kind of the high pitch noise you can see. You can observe, you can hear a high pitch noise here, high pitch sound. Why is that? Due to the, when you consider this M value, this one's M is much higher, the length per unit, sorry, the mass per unit length is much higher. As a result of this one, higher this one, lower the frequency. That's the next reason here, right? And how this tension? Obviously we know, guys, there are a few nails here, we call them as keys here, right? We just rotate them, or we just tune them, or we just rotate them to compress it, or we can just simply increase the tension of the string using this, or we can just reduce it if you want, right? So when you press it here, the tension of the string can be increased, as a result of that. The frequency also gets increased, right? So let's increase it. That's the point here, guys. So that's all about this instrument. But I know here much more complicated stuffs are there, right? So I hope this is all of those things properly through my videos here. Yeah, so let's meet soon again with one of my lovely videos, guys. Have a nice day. Just post my videos and everything, just refer. And if you have any sort of problem, just comment section is available. You can upload, or you can just not upload it. You can just ask in the comment section, and I'll get you back with one of my lovely answers if you want, right? I'm totally approachable and I'm willing to answer any sort of question. Thank you very much. See you guys. Bye bye.